So this is what you get. So based on this, sometimes it's not easy to see graphically what is the flow. Okay. So UR and U theta, just based on this, by looking at this, of course you can make out. Some people with experience you can make out. The best way to do this is one way is I'll just try to explain. I'll take this. I'll try to write it the usual way, like you do. Once you if you is to convert them into. Let us look at this. What we have is phi x in Cartesian coordinates. You have a Cartesian coordinates. U is equal to uv in Cartesian coordinates. Okay. So I think let me use it. I'm not using it here. So u equal to uv. This is Cartesian coordinates. So this I want to go to other coordinates. This is same u bar that you are writing u r u theta in polar coordinates. So what is the meaning of this? So this is your u I cap plus v j cap. Okay. So here u bar equal to u r into r cap plus u theta into theta cap. This is what you have. Now to see the flow, for example, and you know this velocity component. So I can get my directly my streamlines. Stream, right? ST streamlines. How to get my streamlines? Streamline psi of xy is anyway two-dimensional flow. So how do you get your my streamlines? Dx, you can either solve it dx by u equal to dy by v. Okay. Of course, you can always involve z by 0. This is what you do. Okay. So this you solve it. You know what is uv. If you know as a Cartesian coordinates, u of xy, v of xy. If you have, you solve this simultaneous ODEs and get your psi of xy. So then what are your streamlines? So how do you see the flow? Flow is basically you draw these things, xy equal to constant. Those are your streamlines, right? Finally, those are your streamlines. This is the flow. You draw them by drawing psi equal to c. But what you have here is only ur and u theta. So you need to convert them to Cartesian coordinates. That is one way. Okay, this is only one way. So I'm just giving the first way. First way is drawing the streamlines. Okay. So in this case, what happens in the conversion case? What is the streamlines? dr by ur equal to what is the other one you will get?
d theta. Sir,
r
1 by r.
d theta. R d theta divided by that
Yes,
is what is your r d theta divided by u theta. Of course, this is enough, no, for you to get it. So you don't really need z. If you want z also, you keep it dz. You are using polar coordinates means is cylindrical coordinates. If you solve this one, you solve this one directly. Okay, this is what is relevant for you. So you solve these equations, you get your streamlines. This is one way. Now I can draw same flow. So flow, both the cases, flow is this only. This is one way. Or I simply suppose I have u and v. I have phi of phi of r and theta, that you know already solution. Velocity potential I know, right? So now go directly into function of xy. You can do that, right? R equal to x square plus y square under root. Theta is tan inverse y by x, or sin theta cos theta. You can always write. So you convert them into, once you know phi is phi of r theta or phi of x comma y. Solution. This solution, what you do now directly using this also I can do. So once you get this one, convert this into phi of xy. Then you know u equal to dou phi by dou x, v equal to dou phi by dou y. This we know, right? This v, this is u, the other component. Okay. Once you know this, you know what is uv, right? So No. Why should you calculate this one? So this flow, if you want, you don't need to even do here. Once you convert this into function of x, y, you draw it directly. You draw it. You can draw directly, right? Phi of x. So what is the flow here? If I look at the flow, actually it's not flow. It is something else. Opposite to the flow. Okay. So I would say perpendicular to the flow. Perpendicular to the flow. Perpendicular lines to the flow. So what are these lines you call potential lines, no? Stream lines. What do you call the other one? Other lines? Equipotential. Equipotential lines. You draw them directly. So what are those? Phi of xy equal to constant. You draw them. You draw these things. So once you draw these things, for example, you simply example if you do, if you simply take source flow you want. Source you know, right? So what are the equipotential? Basically circles. So if you actually see this one, that is what you will get as a circles here. Okay. So immediately perpendicular to this only I need in the polar coordinates. Okay. So directly I am drawing this or phi of r theta equal to constant. So if you draw this one, this is what you are seeing. So both the things, phi and psi, are perpendicular to each other. Phi equal to constant, any constant. That curve is actually perpendicular to psi equal to constant. This is another way. Okay, directly you are doing. So one is calculating the streamlines. Other one is this one. And what is the other way? So this is by, we are not doing anything. Directly we are doing it. But you have to take the opposite curves. Okay, the perpendicular curve. So what is the third way? Third way is just looking for stream function. Just like here we have already phi. Just look for the stream function. So that means you already have ur equal to. So you already know. So given that this is known, ur u theta given is known. Okay, known, for example. So once you know this one, first thing is I can convert this into dou x dou y. Okay, so how do I get this? This implies what is uv? What is uv in polar coordinate, in Cartesian? So how do you get this Cartesian?
We can use x equal to r cos theta, y equal to r sin theta.
You have now, see, we have done that converting Laplace equation into polar coordinates. If you use that one, for example, let me do this, the simple calculation. This, okay, so this just as a proof for you. Simply start with dou phi by dou r. Okay, phi is a function. Okay, let's call this some phi. Okay, phi is your potential function. So dou phi by dou x is what I want in terms of dou r, dou theta. So you will get, what do you get here? Dou phi by dou x.
Dou phi by dou r.
So I don't want dou r. So let me write it as dou r here itself. Then I'll take the inverse. Okay, that is easier because otherwise dou phi by dou r into dou r by dou x I want. So dou r is like a square root. No, that derivatives will be a little complicated. I don't want to complicate it. Easy way to do is dou r I am writing in terms of dou x dou y. So dou phi by dou x into dou x by dou r plus dou phi by other component dou y into dou y by dou r. Okay, I simply see basically d phi I am writing total derivative of phi as a function of r and theta, xy, r and theta. We are writing like this. R and theta are in terms of x and y. So composition, this is what is the total derivative, and divide by dou r. That's what is this one. This will give me what? Dou phi by dou x by dou r, x equal to r cos theta. Okay, so x equal to r cos theta, y equal to r sin theta. So you do dx by dr is basically will give you what? Cos theta, right? Cos theta dou phi by dou x plus dou phi by dou y, and dy by dr is sin theta. Sin theta dou phi by dou y. That is what is dou phi by dou r. So what happens to this one? Dou phi by dou theta equal to, do the same way. So I want dou phi by dou x into dou x by dou theta. So what is dou x by dou theta? Minus r sin theta. Plus dou y by dou theta. What is dou y by dou theta? R cos theta into dou phi by dou y. Instead of dou r, I have dou thetas. Okay. Dou x by dou r, dou y by dou r places, I have dou x by dou theta and dou y by dou theta. So that's what I wrote as here. So these two equations, you solve them, right? If you solve them, what do you get? I will get dou phi by dou x, dou phi by dou y. So this is exactly your u. This is your uv, which is equal to, what is that you get? That matrix times, right? So you invert that matrix. You write it like ax equal to b. Okay. You look for x is basically dou phi by dou x, whatever you want, dou phi by dou x, dou phi by dou y. That matrix, you bring it to this side, invert it. Once you write that inverse, and what is that you write it here? So that is going to be 1 by determinant. Determinant will be r for that matrix. And you will get, I'm writing directly that inverse. Inverse to dou phi by dou r and dou phi by dou r and dou phi by dou theta. So what are these matrix involved? Once you invert it, you just do that calculation. I'm writing directly. So I'm writing here r cos theta minus sin theta, and here r sin theta. You see that minus b minus c we are writing now. So in the inverse, this is your one. This becomes positive, and here your AD becomes dA. No, so that's what you are saying here cos theta. Followed? So
Yes,
that's
sir.
all. So this is another way of looking at it. So now finally, what is that you get? So this, if you write it as a two components, so you simply write it as components. Cos theta phi r minus sin theta by r into phi theta, comma, sin theta into phi r plus cos theta by r into phi theta. Done, right? This is what is your uv. So once I know my uv, what is that you are trying to do now? What is the third way of looking at it? So once I know my uv, you know what it is, right? So once you write in terms of uv, convert them. So these are your Cartesian coordinates. You convert it, right? So once you get this one, phi r, you calculate whatever you got, theta, everything will go. Even if it is there, you convert into xy. Basically, these are Cartesian. Okay, these are your Cartesian coordinates in Cartesian. In Cartesian coordinates, you have. That's all, right? Once you know uv, you can draw them directly, right? So when this is useful, for example, yesterday we have seen that uniform I was telling, no? You actually get uniform flow parallel to x-axis. What is that you have? Yesterday, what is that flow that we have given? N equal to 1 we have given, no? That a1 cos theta and another one is minus a1 sin theta or something, right? You try to do this one. You put it here, that everything will go. Thetas will go. Finally, you are getting only one side only. So only x, some constant times x, comma, another one will be 0. So this component will be 0. That is actually uniform flow. Okay. So just recall and give me that one. What exactly example? Let me write it. So if you have a phi, what is the phi that you have? Phi of r theta equal to, yeah, give me what is that flow that we have taken n equal to 1?
Yes, sir. A power n, generally is a power n cos n theta, sir.
No, put n equal to 1. The whatever, oh, you don't have that one, that file, right? So let me open here. So yes, I will show you here. So yeah, so what is that flow? That, see, first we've done this. After this, I think somewhere, yeah, this place, n equal to 1, a1 cos theta minus a. So that is corresponds to, what is your phi? Phi is a1 r into cos theta. So A1 or cos theta basically, right? There itself you have, right? So A1 or cos theta. That itself tell you that A1 x only, right? Right? So what is this? This is nothing but phi of xy is A1 into x. Finished. Dou phi by dou x is constant. Dou phi by dou y is 0. You can easily see, no? Right? No, I can directly write this one. So, for example, like yesterday, like I did, here dou phi by dou r. What is your UR? So how you are getting UR? UR is basically that grad phi thing you are writing in terms of that is different and this is different. Okay, that you see whatever dou r and dou theta with some components only it becomes orthogonal. That's what we have done. That the orthogonal Cartesian orthogonal curvilinear coordinates. So curvilinear coordinates. What is your UR? UR is what is UR? Dou phi by dou r.
Yes, sir.
Dou phi by dou r. If you do this here, this becomes minus A1. No,
Sir,
just A1, right? Plus only.
A1 cos
A1,
theta.
A1 cos theta. What is U theta? Minus 1 by R times RR goes
Yes.
minus A1 sin theta. This is what you get, no? So now you try to substitute here. What happens? This implies UV is what? This implies anyway, UV is what? If you know this one, what is UV? UV is A1, this is 0. Now if I'm using this formula, let us look at this. Cos theta into phi r. What is phi r? Phi r is your UR, no?
Yes, sir. A1 cos theta.
A1 cos theta. So it becomes A1 cos square theta minus sin theta by r into what is phi theta? So phi theta is minus r A1 sin theta because 1 by r dou u by dou theta is right. 1 by r dou theta is actually right. Dou phi by dou theta is actually your minus A1 cos theta. So that r you bring it this side. This r gets cancelled. So you actually plus this is actually what it becomes plus sin square theta plus cos square theta equal to 1. So you actually have A1. A1. That's all right. So simply A1.
Yes, sir. Yes.
What is the other one? You see that is going to become 0. So here, if you use this one, sin theta into A1 cos theta. So A1 sin theta cos theta, and this becomes minus cos theta into sin theta into A1, of course. Okay, this becomes 0. So both are same. Okay, so this is basically uniform. You can easily flow. See, these are the 3 ways to look at. Okay, so these are the 3 ways you can directly see. Okay, this is one way. One more way is what is the one more way? Can you that we have already asked you to do? What is the 4th way of seeing the flow? You write in terms of stream function, right? Stream function. So what is the stream function? If you are known that U theta are known. So what is the 4th way? So if this is this one in polar coordinates, then stream function we know. Okay, what is the stream function? So if they are in Cartesian coordinates, you know what is the stream function. Okay, so in this case, what is the stream function? U are equal to
1 by r dou psi by dou theta.
1 by r
Dou psi by dou theta.
Yeah, dou psi by dou theta, and then U theta equal to minus
dou psi by dou r.
Dou psi by dou r. So where psi is stream function. This stream function, because it's unique in the 2 dimensions. Stream function, stream lines, you little be careful. They're different. Okay, that's all. This is one thing, and this is equivalently you can put it if U is given as U and V, that is in Cartesian coordinates. Then what is your U equal to dou psi by? This is that is in polar coordinates. This is a stream function in polar coordinates. This is your This is what dou psi by dou y, right?
Yes, sir.
And v equal to minus dou psi by dou x. Correct? That's all. So you get your where psi is Cartesian stream function. So this way, so implies you basically get psi of xy equal to you're getting r psi of r theta. Put them constant. Those are your streamlines. Implies streamlines. These are the 4 ways of looking at this. Whatever I have done yesterday. Okay. So let me open that other file, that whatever we were doing yesterday. So that yeah, look at this one here. Now if I ask you to do this one, so n equal to 1, u r equal to a1 cos theta minus a sin theta, that gives you uniform flow. Okay. So I wrote in, I could not see directly there yesterday. So I will put it like it is actually simple uniform flow going in the direction of x. Okay. This flow is actually, this is like this, x direction. This is y direction. Okay. Fine. So a1 is constant, that gives you that one. So what is this one? Psi equal to, what is the psi lines? Y equal to constant, right? So whatever, now we can replace immediately. So what is psi equal to? What is psi in polar coordinates? What are these lines in Cartesian coordinates? Uniform, parallel to x-axis. Y equal to constant, no?
Yes, sir.
So r sin theta equal to constant, right?
Yes, sir. Yes, sir.
So r sin theta, that is your, basically you get r sin theta, right? R sin theta, yeah, you should get something like r sin theta. R sin theta is y, no? Yeah, that's all, into constant, right? So this is equal to constant. So yeah, this is your stream function. So psi equal to constant, those are your straight lines. So that means so that straight lines. So equal to constant, right? You have to put like equal to constant is a straight line. Okay. Understood now? Hello?
Yes, yes, sir.
You ask me the question if you need something. So this is what is corresponds to n equal to 1. So n equal to 2, if you do, this is what you are getting. Now you have u theta immediately, right? So you can do this ux u. Yesterday I explained, in fact. So this looks like planar flow. So you can easily see by the same way, one of these methods that I have given, or directly you solve those streamlines. You can write the streamlines, or directly your phi x itself. So phi xy, what is the phi xy here? If you do, what is the solution? N equal to 2. What is your phi?
A2 r square cos 2 theta.
Yeah, a2 r square cos 2 theta. a2 r square cos 2 theta becomes phi of xy equal to a2 r square cos 2 theta. This is r theta, right? So this is in r theta. Phi of r theta. You convert this into Cartesian coordinates. Cartesian coordinates, what it is? This is simply a2 xy only, no? R cos theta. No, not this one, right? What is that you get? R into cos square theta minus sin square theta, right? R square. R square cos square theta is what? X square, right?
X square minus y square, sir.
Minus y square. So these are your equipotential lines. Equal to constant, you put it, equipotential lines. So these are x square minus y square means what? So what are x square minus y square? So if you draw this, they are lines, no? So
Yes, sir.
perpendicular to this, those are your, these are perpendicular to, these are the lines. I have to draw in some other. So these are like x square, x minus, x equal to y and x equal to, so these are your lines. So these are basically, this is how you get, those are lines, right? Line equations. They are perpendicular to the actual, the planar flow, whatever you are seeing. You understand? So these are equipotential lines. X square minus y square equal to constant will give you simply like a crosses in the cross passing through 0, 0, right? So these are the lines. These are the lines. So your actual, these are your equipotential lines. The perpendicular to these lines means those are your, that's how it looks. Okay. That is your extensional flow, planar extensional flow. That's what you see here. Now you convert this into, you take n equal to greater than 3. So you try to do the same thing. So you can easily see between the angles. So the angular things, between the, see, this is what is n equal to 2 means you have considered between 0 to pi by 2 perpendicular planes. Okay, between them you have the flow. For example, if you look at only in the first quadrant, if you do in the 3, you take n equal to 3 and you see this pi by 3 between the angles pi by 3, you will have a flow, same flow, similar flow. Okay. So that you can do by the way, whatever I explained. So whichever method you follow and try to see that they are actually similar to, these are all extensional flows. Okay. Shall I leave it here? Fine, right? So
Yes, sir.
why we are doing this? We are mixing. So far we have given. So what are the other things that we have? So look at these equations. Now what are your solutions? So where is your solutions? Solutions basically coming from 21, no? 21, what are the solutions that I've given? Lecture 21, the solutions of your these are your solutions, right? So log R you have seen. What is log R? Log R
Log
gives
of
you,
x square. Yes.
yeah, that's what is that one? The equal to constant means x square plus y square. Those are circles for your equipotential lines. Those are source. So this is your actually source, right? Source or sink. N equal to 1, r cos theta, n equal to 1, n equal to 2, r power n cos n theta we have seen. Wedges, okay, those equivalent, this one. But if you take b1 cos theta, if you do, what is that you get? N equal to 1, b1 cos theta by r sin theta by r. That also you have done, right? What is that you have done? So yeah, this is the one corresponds to this. If you look at the other term, if you do b equal to n equal to 1, so what you got is actually doublet flow. That gives you doublet flow. So but it's not easy to see. Okay, so this doublet flow is not easy to see. That is, see, if you actually draw this, you try to convert this into that uv, okay, or you simply put it that way. So if you convert this into polar coordinates, in Cartesian coordinates, what is this one? b1, what is that you get? What is your phi of xy? Phi of xy equal to b1 divided by r square, that is x square plus y square. Okay, and r cos theta is simply x. So can you draw this x divided by x square plus y square equal to, what is this one? Yeah, you put equal to constant. What is the meaning of this? This is basically x square plus y square equal to some constant times x. That means, what is the meaning of that? Those are, what are the equipotential
Doublet.
lines? No.
Doublet.
That equipotential lines, where are they? They are basically, if I draw, no, I'm just spoiling this one. I'll not, I'm spoiling, but I'm not going to save this file 22. Okay. Oh, maybe I'm actually spoiling. So let me draw it somewhere here. Okay. So what you are drawing is equipotential lines. So what is this one? This is equal to constant x square plus y square equal to some b1 by c into x, right? So that x you can absorb into x square. That is actually circle equations only, no? So you basically have circles. These are your
Yes,
circles,
sir.
right? So circles means here, whatever the circle radius may be, whatever you don't know, right? That increases. So those are your circles. Circles everywhere is based on those. If you for this, its opposite lines are basically doublet. This is what you will get as if this is your flow. All these circles, wherever you put a circle, okay, circle on the x-axis, whatever may be the radius, will be your equipotential line. It's perpendicular. Can you see that one? Can you feel at least?
Yes, sir. Yes, sir.
For this circle, whatever I draw now, all your flow lines, the stream lines are actually perpendicularly crossing. Okay. So for example, here, this is perpendicular. This is perpendicular. Okay. So this is perpendicular. Like that. That's what I mean to say. Okay. So these are equipotential lines. Directly you can see. Of course, you cannot see. I only get the circles here. How do I see the flow? Yeah, then you are not able to see immediately what is its perpendicular thing. Then you try to calculate psi, right? Or streamlines directly. Directly streamlines. You have u or u theta. So you calculate streamlines. How do you get the streamlines? dr by ur equal to r d theta by u theta. You do that one and try to solve this one. You get your streamlines. Then it will be your doublet. That is one way of seeing. So, or the best way to, so how do I see? That is what you are calculating the streamlines and trying to put them. Now what I do is, you are trying to, I can construct that one. Actually, it is not something you created. It is actually already you know something in source and sink, no? Those log functions if you take. So for example, you need not take minus epsilon, put it at 0. Simply put one source sink at 0, source at epsilon distance. As epsilon goes to 0, what happens? That source is coming to 0, 0. That is where the sink is there. Okay. So that becomes doublet. So that's what we have seen mathematically. So when you consider this way, so as you see, you are making, only thing is a strength of those two sources, source and sink. You're trying to make that it is going to be infinity when they are coming together. Okay, in such a way that strength into that distance is actually constant. That is the strength of the doublet. Okay, that q into epsilon or q into 2 epsilon here, that is actually the strength of your basically divide by 2 pi you put it. So that's what the constant will go. That is actually your strength of your doublet. This, if you actually see this one, lambda by r, you want to see how does this look. Okay, so finally you get this one. This is earlier, what do you get? Earlier, what is the doublet that you are seeing? B1 cos theta by r only, no? So here also you get the same thing, lambda into cos theta by r. So same flow. So it's basically doublet. So doublet, you can get it, you can see it this way also. Two sink, one source and sink, put them together, so make a doublet, just like in the electrical electronics, no? So here you do physics, you see somewhere, no? In electronics, you see two charges of, you put them together and then it becomes a doublet. Okay, it will have their physical meaning. Is there some doublet moment, all those things, it finally eventually it becomes like a doublet. Okay, so that's charges, even if you put it, it comes back to that acts, forces act in opposite direction and turn, it becomes that way. Okay, that's a doublet. So similar thing is happening here. That's what you are seeing as a flow. Okay, so I wrote here something different because you can't write this you need to see here. You simply ur is different and u is different. So yesterday, if you do this, these are u or u theta, right? So if you convert this one, I think these are all okay, no?
Yes, sir.
Yeah, I think these are all okay. So you divide by this. Yeah, you can. I convert them into u or u theta. I convert them into uv. Those are your components, no? Can you do that?
Sir,
This you cannot do. Why? Can you tell the reason? You have a transformation now. You have a
convert
transformation. You need to convert them using only by the transformation. Okay.
Yes.
So this
Yes.
is actually wrong. You can't do this way. Do you get this point? Yesterday I made a mistake. You see, you simply u r u theta. Those are your UV components in that curvilinear coordinate system, polar coordinate system. U r u theta. In that direction, you have velocity. Now simply replacing r cos theta by r sin theta by x and y, you don't get your Cartesian coordinate. You have a transformation there, right?
Using that
Because
formula.
yeah, so you have to use u r u theta. You use u r u theta like 1 by r dou phi by dou theta, right? Those things you use. How do you get this one? So what is u theta? This is another way of using psi as a stream function. So how do you get this u r u theta? So how do you get u r? By the way,
So, del psi by del theta.
yeah,
By,
this how we get this u r u theta is because grad phi equal to that we have done in the curvilinear coordinates 1 by
u.
hu is 1 into dou phi by dou r into er plus and 1 by hv. What is hv? Here we will get r h theta. Okay, e theta component 1 by hv. V is theta here. 1 by h theta is 1 by r and dou phi by dou theta. So that is why phi is this. Okay, I mean this is not f, this is phi. Okay, so dou phi by dou r equal to u. Okay, 1 by r dou phi by dou theta equal to v. Right. So what is this one? This will give me, this is your u r e r cap plus this is your e theta into u theta into e theta cap. So these are your u theta e theta. Okay. This is basically what you have is u I cap plus v j cap. Simply putting r equal x equal to r cos theta, y equal to r sin theta will not make this possible. That is what we have done wrong here. Okay. If you want them, you have to use that formula, that matrix I brought now. That is what you have to convert. Okay. Did you understand what I'm saying?
Okay, sir. Yes, sir.
Okay. Others, please, if you don't follow, just let me ask. Okay. So once you get this u r u theta, you try to convert them. Okay, uv or whatever way you like it, uv you convert this. This is different, that is different. Okay. So if you know u r u theta, try to get psi or try to directly get your phi. Here directly here I can substitute phi of r theta, phi of xy I can convert. Here there is nothing here. Okay. So here immediately I can make it as phi of xy. What is phi of xy? Lambda times divided by x square plus y square times r square. Now this is x. X divided by x square. This is what these two are. This here I can do, but not here, not the velocities. Okay. So what is the other one that we have done? So a power n r power n cos n theta. So for n greater than or equal to that, yeah, this we have done. No? So this I think you understood. So for n equal to 1, it's uniform. N equal to 2 is planar extensional flows. So so all these things we are trying to construct fundamental flows in the mind. Motivation.
We can,
Yeah.
sir, if we can directly convert in phi of r theta into phi of xy, just replacing the x equal to r cos theta, y equal to r sin theta.
That is the
From
best
that
way.
phi of,
Only yeah, you can
yes, sir.
directly get the equipotential lines. Perpendicular to that, you have to draw the curves. Those are your streamlines. That is your flow.
Yes, yes, sir. If
But
from that,
sometimes you may not be able to see that one. No.
yes, sir.
For
Yes, sir.
example, you got the circles. Sometimes I showed you circles, no, for doublet. But how do you know exactly? If you draw carefully only, you can realize that doublet thing. Otherwise, may be difficult to visualize. So that is the best thing is, that is why we are trying to do in a different way, not the usual way that all the four different ways that I try to put it today. Instead, you see it as same thing as two, one sink and one source. You put them to come together, so you can feel that whatever goes out and finally ends up in the sink. So it is like circles up and above, below, and so I can get the feeling of that. this doublet coming from source and sink, right? So if I put the source is going out, finally it's coming to sink at the same point. You are bringing it to the same point. So like that, even below also, right? This is this way and this is this way. So this is what you are seeing, isn't it? You understand what I'm saying?
Yes, sir.
Where did I do this doublet thing? Uh, take two sum, right? So I try to, no, this is today thing I've done. Where is that? This is 21, 22, I think. Yeah, so where is the doublet thing you have seen? Yeah, here. We put no source and sink, put them together. So here. So you try to see from this graph, whatever from this figure, you see, you can easily see the above. Those doublet streamlines, you can get it. So whatever goes from here, it will end up here. You bring them minus m plus m, minus epsilon, bring it to 0. What will happen? It looks like that circle only, no? Those circles above the x-axis, below also. So that is the reason we try to do this way, just to visualize that flow. So one source and one sinks, put them together, it becomes doublet. It is matching with your physics electronics. That is where you use the two potentials, two charges basically. Okay. So are you done with all the solutions? Hello?
No, not complete, sir, because we don't have that PDF, sir.
No, not you. I am asking whether we have done everything. This R power and cos theta we have done. R power minus 1. Only in this case, only minus 1 only we have done. What happens when n equal to 2, 3 and so on, divided by R power n? Cos 2 theta divided by R square. I think it will not give you any flow. Okay. So can you just try to do that one?
Okay, sir.
Yes. So so today is actually Thursday, right? So tomorrow I'll try to create. So what time you are free?
Evening, sir, 6:30 to 7:30, sir.
Okay, so the same way I will do 6:30 to 7:30 tomorrow and day after. Okay, so
Yes, sir.
we have time. So let me do now actually what you want to do today. So we'll do so the main motivation, as I'm trying to tell you, here you make a uniform flow. I allow the uniform flow, and I want a circle. Let me put finally. I want circle here. Okay, what is this circular? You can see it as cross section. This is like your r and theta. This is your x and y axis. Okay, that means is r and theta. Okay, and opposite to the screen that you are seeing, and that is actually your z axis. In cylindrical coordinate system, you can imagine a cylinder, circular cylinder. This is the uniform flow. So eventually what happens? So how do you visualize this one? This flow, it will become like this, right? Is what you expect. So how do you get this flow? So what I try to do here is that this uniform, you make a uniform flow, okay, and then plus what I try to do, I make a doublet. If you do the doublet, so what is the doublet that you have? No, say here. This you try to add them. So what do you expect? So what you expect is like this. So inside this circular cylinder, so let's whatever here, okay, this is the circle thing. What happens here? Inside the circle, you actually have the doublet. Okay, but everything is confined to only in this circle. Can you believe? And then whatever here, so can you feel it? And this goes like this. So we will actually get this this one. Okay, So you see this one, there are some stagnation points. So this is one, this is the one, and this is the one. So whatever this circle, no, so this circle, whatever the circle, the flow is not actually penetrating. This flow outside this circle, inside the circle, two different things. So that we constructed by putting doublet and uniform flow. So whatever is inside this doublet flow in that uniform, that circle, this is a stagnation point. Okay, we'll understand that one through that stagnation point. What is the meaning of stagnation point? To understand the flow, we are trying to bring in the stagnation point, the concept of stagnation points. So what are those points? The points of R. So we are dealing with only in the polar coordinates. You consider R and theta. So let's call this. So that is where U R of R star and theta star equal to 0. Similarly, U theta of R star into theta star equal to 0. Okay. Where R star and theta star are stagnation. What is the meaning of this? Basically, the flow velocity will be 0. Okay. So once you know, you understand that there is a flow, this is the stagnation point. Something you will get it, some point you will get it. So passing through, once you know the stagnation points, let us say one point is a stagnation point. What is the streamline passing through? Passing through a stagnation point. So if you understand that one, this is your stagnation point, R star, theta star. Okay. You look at the streamline passing through that one, that gives you exactly your circle. Circle, no, that whatever that circle that you are seeing, okay, this circular thing, that is actually your streamline. That is also a streamline passing through that. We will actually show mathematically. And then you see that inside flow, outside, inside is not affecting the outside flow, inside that circle. So the whole doublet you can replace it as a solid cylinder. Okay, that's a solid circle you can put it. So you remove that doublet thing, and what you are seeing is if you allow the uniform flow, and instead of doublet you put a circular cylinder, solid cylinder, flow is not penetrating, just going separate, right? Just outside the cylinder, flow goes. This is the potential flow. Okay. So after all, this is not the reality, it is only potential flows. Fast cylinder, circular cylinder. We are only looking at the cross-sectional thing, only two-dimensional thing that we are seeing. Have you understood the whole idea? So that this is what I'll try to do the next class. Okay. So understand this one, and slowly. This is done at two stages, 1 and 2. So these are the two crucial points. You understand what is the meaning of stagnation points. Through the stagnation points, you try to understand the streamlines. That is what separates the flow inside and outside. Basically, here doublet and uniform flow you are separating. So the whole doublet you can remove. So it is independent now. So you remove the doublet. You see, remove means what? It's basically you have a stagnation point and then you have a solid thing. That is your streamline, no? So obviously, if you have any in the flow, you put some solid object. Streamlines are basically that boundary is also streamlines, right? Yes or no?
Yes, sir.
Yeah, so that's basically the reason you put that solid cylinder. So we'll try to look at this thing, and finally we'll try to calculate the forces on this. So before with that, so we still have little time. So what I'm trying to do now here is little bit about Laplace equation. Okay, so far Laplace equation. I only gave the solutions, right? Just to spend this 4-5 minutes, let me understand. So what is the Laplace equation? Laplace equation you try to solve. Okay, so here, this is your del square phi equal to 0. Okay, Dirichlet problem, you know that we have nothing to do with the fluid dynamics here. So we don't care what is the phi value, right? That is not relevant, right? You don't know phi on the boundary, right? Hello. Suppose this is your solid object, inside fluid is there. On the solid object, you have what do you have? U dot n, no? that u dot
Yes, sir.
n equal to 0 or whatever you give. Suppose this is 0 if it is a solid object, or u dot n is actually what? Equal to some velocity dot n. What is this one? Actually, you have this solid object is moving in a flow. This is the condition for some flow is there. Inside there is a fluid. On the surface, it is like a fixed object. Okay, you have a flow. This solid thing is not moving. Fixed. Okay, fixed means this one. This is the meaning of moving cylinder. Okay, moving. This is moving. Okay. So what are these? These are u dot, for example, you consider n cap where it is fixed. What is this one? This is actually dou u by dou n equal to 0. Okay. So once I write this one, you try to write it like dou square. So del dot u, right? So the del dot u means this is basically inside del dot u equal to 0. That is coming from your flow. What is this one? This is actually equal to your Euler equation, or del square phi. So this is your del square phi, right? What is this one? This is actually equal to dou phi, right?
Yes,
How
sir.
do you
U
see this
equal
is
to
actually dou phi by dou n? This is actually equal to a grad phi. Grad phi is your u dot n cap. Okay, so this is nothing but your dou phi by, this is your directional derivative. So this is equal to 0. That is what it becomes, this condition or that condition. So it is relevant in your fluid dynamics. It's relevant for the Laplace equation with boundary condition being dou phi by dou n. This is a Neumann condition, you say. Either it is 0 or something else given. Okay, it's given on the boundary. Here del square phi equal to 0. In this case, the solutions are unique up to a constant. Have you studied this one? You must have studied now in PDS. Did you not? See, when you try to solve this one, you will get any constant is always satisfying. Given means, for example, equal to 0, for example. Okay, you have some, let us say some object where heat transmits. Solid steady state heat equation is basically Laplace equation. Outer layer, suppose on the boundary you insulated them. That means you are not allowing any heat to go out or letting inside. That is basically saying that flux is 0. Dou phi by dou n, that heat flux is no, you're not allowing to go out. That is what is the meaning of Neumann condition. That is 0 Neumann condition. That is the insulation. So in that case, if you can easily see that phi, if I put any constant, suppose you have a solution phi, I add some constant, still it is a solution, no? Because it satisfies. That constant is anyway a linear equation. So I can add and subtract. Constant itself is a solution. So basically up to a constant means that one. But constant doesn't matter for you in the fluid dynamics because phi equal to constant. I can always I can add a constant, any constant, but finally you are going to take the derivative to see the flow. So that becomes 0, right? Isn't it? So this is what you do. So you're only looking at the Neumann problem for Laplace equation in fluid dynamics. Of course, if your solid object is solid, is only this one. That's what we look at it. If it is some some kind of boundary where you can have a combination of Dirichlet and Neumann, okay, that is Robin conditions. For example, porous conditions, porous kind of materials, different materials you may see different boundary conditions. As a first course, you are not going to look at that one. Okay. So this is what we will do. So this is relevant. So the solutions are actually unique up to a constant. So fluid dynamics point of view, solutions are relevant. So it's unique solutions. Potential flow solutions are unique. That's what you are seeing. You understand? Okay. So you have class or you're free now?
I have class from 12 to 1, sir. Artificial intelligence.
Okay, fine. So any questions up to here? So you try to understand. So I'll now try to put that 22, 23 for you. I am not really organized because I somehow hurried up yesterday, and so that I have to explain all these things now again in an organized way. I hope you understand. If you have questions, let me know so that I clear. So that tomorrow I'll try to look at this flow. Okay, this is called flow pass cylinder. This flow we'll try to look at it in a organized way, and we'll clear this. and we systematically go next class. Okay. Tomorrow evening only, no?
6:30 to 7:30, sir.
6:30 to 7:30. I'll make it and I'll share you this one. Okay. See you tomorrow.
Sir,
Please,
when will you come Idol, sir?
which one? I'm coming. I'll be there on Monday.
Okay, sir. Okay, sir. Thank
Monday
you,
I'm there. So we will see. I'll try to cover these potential flows coming from these solutions. In given P, what realizing the flow, so that flow past the cylinder. Same thing we can do now. Whatever we are doing now, flow past cylinder, these things, same thing we can put it in a complex variable setup. How do you put that? Phi plus I psi. That is your complex flow, complex potential. Now you work with both potential function and stream function. Put them together, you have a difference. All same sources, sinks, doublet, everything you can see there also. But that is what is mathematics that I want to cover fast. Okay. So try to understand these flows and this one. But the fluid dynamics point of view, both are same. So either this way or that way, both are same. Actually, it's irrelevant. But you need to understand, you need to connect your complex variable methods here in the application. So you need that also. Sometimes that may be useful. You can't see this one. See, right now, we're looking at these simple flows. I can see both ways. Either, no, I don't need really complex. I don't need both of them, phi and psi. I need only phi or psi. If I know phi, I can get my UV. If I know psi also, I can get my UV separately. So when you combine them, it becomes complex. So sometimes complex variable methods where your complex flows, I mean complex potential, working with complex potential may be a little sophisticated. You are doing the same thing, but there also you will have little extra things that you will get it. Okay. So some circle theorem, Milne-Thomson circle theorem, those things will come. So we'll look at that one. Okay. So I want to cover. So once I come there, I want to cover this complex variable method and plus this one, flow past cylinder, whatever is required, so that once I come back from there, from Mizoram to here, I want to start this. What is that one? Navier-Stokes equation. So involving viscosity into the fluid. So that Navier-Stokes energy equation, some simple flows and some boundary layer theory. So that is the course. So you need to at least initiate it into that. Okay. So mathematical point of view, these are the things that I do this week and next week. Those are important. So even when I come the next week, I want to take 5 hours so that hopefully I'll try to finish most of these potential flows involving both phi and psi and phi separately that we are doing anyway. Tomorrow day after, I think I'll be finishing mostly a flow past cylinder, whatever is required. Okay. So let us see tomorrow.
Okay, sir. Thank you,
Okay.
sir.
Thank you.